And today I'm going to be talking about fast and parallel state machines. So, oops, that's a little bit too big. One second. That's too small. There. So this talk is based off of a paper called Data Parallel Finite State Machines. And probably the first thing you're thinking to yourself is, how do you make state machines parallel? How does that even work, right? State seems like something that's inherently not parallelizable, especially if you have experience trying to parallelize things. But this paper explains not only how to make things parallel, but also fast too. And so we're going to be talking both how to make it quick and parallel. And the way I'm going to be doing that is by dividing this talk into 3 sections. In the first part, I'm going to be implementing a very simple state machine in pure Haskell. But in order to unlock all the tricks in the paper, we need to actually write the inner loop in C and then wrap that in a Haskell API. And so the second part of the talk will be implementing the core of the state machine in C. And then finally, in the third part of the talk, we're going to tie it all together and show the tricks that the paper uses to make these machines very fast and parallel. So if you go to Wikipedia and you'll search, what's the definition of a state machine? In this case, I'm going to use specifically deterministic finite automata. And a state machine has an input alphabet, which you can think of as a set of tokens that you can feed to the machine. And then the state machine can also have a set of internal states that it can have, and it switches between states every time you feed it a new input token. It also starts with an initial state, S sub 0, and the key logic in the state machine is codified using a state transition function, which is a function of 2 arguments. The first argument is the current state. The second argument is the current input token, and then the result of that function is the next state to transition to. And then finally, when the state machine is done, it concludes with some final state, and we can say if the state machine successfully matched that input by whether or not it concluded in one of a set of final states denoted by F. So if I really wanted to, I could actually translate this almost exactly to Haskell using Unicode syntax. I'm not going to do that to you. We're actually going to use verbose names for the rest of the talk. In fact, if I really wanted to, I could even use like a little Unicode multiplication symbol here instead of the tuple if I really wanted to make it exactly like Wikipedia. But here's how I'll actually think about it. A state machine is a Haskell type that has 2 type parameters. So input represents a type, which is the set of input tokens that we can feed to our state machine. The second type parameter is the type of the internal state of the state machine. And then the other concepts are the fields of our state machine record. So for example, the first field is the starting state. The second field is our step function, which is a function from our current state and our current input, and it returns our new state. And then finally, we have the set of accepting states. And this is a minor simplification, but we can actually hide the state type from the user using a cool feature called existential quantification, which says that we don't actually have to tell the user what the internal type of our state machine is, as long as it implements this ORed interface so that we can stick inside of a set. And that's really all we have to do. And so that so from the user's point of view, the only thing they need to know is what input do I need to feed to this state machine in order to be able to run it. The running example I'm going to use throughout the talk, and it's also the first example from the paper, is a state machine for matching C-style block comments. If you're not familiar with C, the syntax is, first you start with a /, and then you start with an asterisk. That opens the block comment. Then you can have whatever you want in the middle of the comment. Then it concludes with a final asterisk, and then another /. And this state machine formalizes that. Each one of these circles represents one state in the state machine. And these arrows represent transitions, which are guided by specific input bytes. So for example, I start the machine on state A, and if I see a /, that means I might be beginning the opening of a block comment. So I would transition via this arrow to state B. And then if I see an asterisk, that means, okay, I definitely found the beginning of a block comment, so I transition to state C. And as long as I'm in state C, that means I'm in the interior of a block comment. If I see a / or X, where X denotes any other character that's not a / or an asterisk, then I just I'm still inside the interior of a block comment. If I see an asterisk, then that means I transition to state D, which means I might be at the end of the comment, but I don't know for sure until I see another /. If I see another asterisk, I still could be at the end of a block comment, who knows? And if I see the final /, I return back to state A, which means I'm now outside of a block comment. And so our file has nothing but well-formed comments if our state machine concludes on either state A or state B. If we conclude on state C or D, that means that we had an opening block comment that wasn't paired successfully with a closing of a block comment. One way you can actually represent this diagram is a transition matrix or a lookup table. This table has 2 dimensions. The top dimension represents possible input tokens, so /, asterisk, or any other character, wildcard. The other index of the table represents the current state, A, B, C, or D. And so given the current state and the current input token, we can just find where they intersect to figure out what's the next state we'll transition to. So for example, if we're on state A and the current input token is /, then we transition to state B, and so on. And then here's an example of pseudo C-like code for how we would run our state machine. We start on state A, and then for each input token named N, we just look up in our transition table based off the current input token and the current state, what's going to be our next state. And once we're out of input tokens, then whatever the state is currently set to, that's our final state. So here would be the corresponding Haskell code for implementing that state machine. So we say, first we have to define what is the internal type of our state machine. We're going to call that state. And before I continue, can people read that, or do I need to make it larger? Is it fine? Okay. So our state type can have states either A, B, C, or D. And remember, our internal state type can be anything as long as it implements this ORD interface, which also requires implementing eq. And then we can actually define our C-style common state machine. So the starting state is A. Here's our step function. And all I've done is I just took that transition table and I turned it into the corresponding step function. So for example, here we see that for the character /, and we can transition to states B, B, C, or A. And then here we can see, okay, B, B, C, or A. I'm just reading off the table into a corresponding Haskell function. And this corresponds to a wildcard match here, these underscores. And finally, the set of accepting states are A and B. And I can use a cool Haskell extension called record wildcards, which lets me slurp all those fields into my state machine record just using .. Very handy. I love this extension. So last thing is, I've defined my state machine, but I still haven't defined a way to actually run it on a specific input. So that's going to be this accept function, which says, if you give me a state machine, which consumes input tokens of type input, and if you also give me a list of input tokens, then I will return true if the state machine concludes on one of those accepting states and false otherwise. And this is set up so that this step function has exactly the right type that we can feed it to Haskell's full-del prime function. Same thing for the starting state. So we just say the starting state of our reduce is the starting state, the reduction function is step, and then the input that we're folding is input. So if we fold our input using the step function, we're going to get our final state. And then we can pass that final state and see, okay, is this a member of our final set of accepting states? If so, then we match. And we can verify that this works by running it on some sample inputs. So if we have an empty, well-formed comment, it returns true. If we have a beginning of a block comment, but not a close of the block comment, it returns false. Same thing for the next example. If we have a program that has no comments at all, well then all of them are well-formed, it's vacuously true. And but interestingly enough, if we have a program with the end of a comment but not the beginning, we'll actually accept that too. It might not be a valid C program, but technically doesn't count as either the beginning or close of a comment. And another interesting case is that in C, you can actually have 2 opening comments followed by a closed comment, and that actually counts as one well-formed block comment. It's a little quirk of the language, because you actually can't do nested block comments in C for that reason. So here I've wrapped this all into a self-contained program, and I'm going to link to these slides in the end of this talk, and if there's a recording, I'll also include the link to these slides in the description of the recording, so you can run and test these examples yourself. So I'll always include a full example for every time that I benchmark this code. And I'm going to benchmark this on a sample file called test.c, and all it's going to contain is a gigantic comment which has 1 billion spaces in between the open and close of a C comment. Otherwise, it's basically the same as the code that I've shown you on the previous slides. And if we run that on that input, so it's a gigabyte large, and it takes about 17 seconds, or about 1 byte every 17 nanoseconds. And so this is actually not really fast, and we can make it much faster by just not using Haskell's default string type, which is a linked list of characters. People who have worked with Haskell know that linked lists of characters are very inefficient, and you usually want to use either text or byte string for high-performance string processing. So in this case, I don't need to use UTF-8 encoding yet, so I'm just going to use byte strings, which is slightly faster. So here, the only change I need to make to my program is that instead of using read file, I use data.bytestring.readfile to get bytes. And then I change the type of my state machine, so now it accepts word 8s. So word 8 is Haskell's type for a byte. And the input is now a contiguous packed array of bytes instead of a linked list of input tokens. So it's a byte string. And then the last change I make is that instead of fold_l prime from data.list, I take it from data.bytestring. And those are the only changes I need to make to my program, and it should be much more efficient. And so the time it takes to process that input is now dropped down to 1.5 seconds for a gigabyte, or 1 byte every 1.47 nanoseconds. So this, we've already gotten like almost a 12x speed up over just by switching to byte strings instead of using strings. But we're not going to stop there. So we actually plan to get much faster performance by the end of this talk. So the question I have for you is 1 byte per 1.47 nanoseconds good? So like, what is the single-threaded performance we should expect for an optimal state machine implementation? Any ideas? So somebody says it's on the same order of time as like doing a mem copy of the byte array. Yeah, so actually I think, so normally the bottleneck you would expect here is that if you encode your state machine as a lookup table, and you have to do a lookup on every byte, then a lookup table will usually not fit in registers. So it might fit in the L1 cache of your processor. So every time you're doing a lookup, it probably will be an L1 cache miss. And the cost of an L1 cache miss can vary between machines, but if let's say the last time I looked it up, it's maybe around half a nanosecond. That could be wrong, but so if let's say we're half a nanosecond, then 1 byte per 0.5 nanoseconds would, in theory, be the speed limit for simulating a state machine. And so we're about 3 times as slow as that, which means we're probably in the right order of magnitude, but maybe we could do better if we tune things a bit more. And so in order to tune things a bit more, though, we're going to have to depart from using pure Haskell. We're going to start writing our inner loop in C, and then in order to be able to exploit some tricks from the paper. Any questions before I go on to that section of the talk? I actually don't remember off the top of my head. So the main cost is doing UTF-8 decoding, and that is basically a lookup in some table. So I'm guessing you're going to pay on the same L1 cache miss per byte character that you need to decode from that table. So I'm guessing maybe twice as slow. I'm just guessing. I haven't benchmarked it in a very long time, so I don't know. Okay, so we can run a state machine in C using the lookup table algorithm, same as from the paper, the simplistic algorithm described in the paper. For simplicity, we're going to only support 16 states for now. The paper actually describes how to take this algorithm and generalize it to up to 512 states. But I haven't implemented the full paper, and this talk is actually not going to describe the full algorithm because it would take quite a while. So we're just going to restrict ourselves to a subset of the paper, which is simulating 16 states efficiently. And so our lookup table has one index, which is all possible states, 16. And the second index of our lookup table is all possible input bytes, and there's 256 of those. So 16 times 256 is 4,096 elements in our lookup table. And then we also need to give it a list of bytes to process. So that's this input argument to our run function. And then the length of that input list, length, and then also the starting state for our state machine, which will just be a byte, but really it can only be somewhere in our first 16 possible states. The actual algorithm is very simple. We just read a byte from our input, and then we perform a lookup into that table based off of the current state and the current byte, and that returns our new current state. And then when we're done, we've processed the whole input, we just return the current state. Very simple algorithm. And we can actually benchmark this as a pure C program if we just wrap it in a little bit of driver code to read in 1 byte at a time using, in this case, fgetC. And then here's me constructing a state transition matrix in C very awkwardly and running it and trying to produce a runnable example. Now, what's surprising to me is that the pure C example is actually slower than the Haskell code. So it actually takes 7 seconds to run. I think the probable reason is because I'm using fgetC. But what really surprised me here was that I tried to do the right thing using block reads instead of reading a byte at a time. And I still wasn't able to get better performance. In fact, I actually got worse performance, which surprised me even more. So I feel like I must be doing something wrong. And some benchmarks later on will show that some evidence that I must have been doing something wrong, because when we wrap this code in Haskell, it's actually going to get faster for some reason. Don't ask me why. But anyway, you're just going to have to trust me that using C is going to pay off in the end, I promise, even though we're taking a performance hit right now. So we can't actually use our state machine from the Haskell side unless we can unless we can serialize things across the Haskell C boundary. So in the Haskell side, we're thinking in terms of functions, but we can't easily or efficiently transmit a Haskell function across the C interface. So instead, we're going to try to transform each Haskell function into the corresponding lookup table that the state machine on the C side expects. So in Haskell, we will similarly hard code the number of states to 16, so it's a giant enum of 16 states. To make things easier to serialize, I'm actually going to split our step function into 2 separate types. The first one is going to be a transition type, which is a function from the current state to the next state. And then a state machine is going to be a function from a byte to a state transition. So if you were to just unwrap all the new types, then this would be our original step function, a function from a byte, and then the current state to the next state. The other reason why is that we actually want to keep the transition type, because this transition type will make it easier to understand what's actually going on in the paper later on when I explain some of the tricks that they exploit. So in order to serialize things, we're going to use Haskell's binary interface, which is one of several classes out there for serializing things and deserializing things to and from byte strings. So for a simple type like an enum, we can actually just derive it using a very handy feature of Haskell called derive generic. Many Haskell type classes are set up so that if you derive generic, then you can also derive other classes like binary. The only thing you need to do is just enable this derive generic language extension, then derive generic, and then the binary class is set up so that it will automatically pick a default good implementation based off of the generic implementation. For an enum like this, what it will translate to is that each state will correspond to 1 byte, which is the number of that state. We can write a function just so we can visualize how the serialization works. So if I serialize state 0, that's just 1 byte, which is 0. State 1 serializes to 1 byte, it's 1, all the way up to state 15, which is byte 15. Now, if we want to serialize a function, like our state transition function, the way we're going to encode that is as a lookup table. So if we have 16 possible starting states, then that lookup table will have 16 entries in it. And we can also deserialize the lookup table back into a function just by having the function look up the byte from that table. And so that's what this handwritten binary instance at the bottom is doing right here. And let's use a contrived example. So I have some state machine where if it's an even state, it transitions to the state corresponding to half of that number. And if it's an odd state, you multiply by 3 and add 1. And so here's the corresponding function that maps that transition. And then here's another transition function we're going to be using later on, the identity transition function, where every state just transitions back to itself. So if we were to serialize these 2 transition functions, we would see that the transition function, this should be, say, contrived transition. If we serialize the contrived transition function, then we're essentially just reading out the right-hand side right here. So 0, 4, 1, 10, 2, ... 14. 0, 4, 1, 10, 2, ... 14. And the identity function will just be all the original states back in the same order. So 0, 1, 2, 3, ... 15. And then we can build on top of that to specify how we serialize the larger state machine function. And we do it the exact same way. We're just building a larger lookup table. Now, instead of 16 states, we have 16 times 256 equals 4,096 entries in our serialized lookup table. And we do so by just enumerating all possible input bytes and then serializing the transition array for each one of those input bytes. And we decode the same way. We just perform a lookup into that original table. So here is a very contrived state machine which says if our current input byte is even, then our transition function will be the contrived transition function. If the current input byte is odd, then we'll use the identity transition function. And then we just go through each byte in order. So we start with byte 0, and we say, okay, well, that's even. So now I'm going to serialize the transition array corresponding to our original contrived transition function. So that's 0, 4, 1, 10, ... 14. The next possible input byte is 1. That's odd. So now I'm going to serialize the identity transition array, 0, 1, 2, 3, ... 15, and just keep cycling between them. And this only requires 4 kilobytes, so that's easy to transmit across the Haskell to C foreign function interface boundary. So here is an example of one last thing. So we want to have a convenient function so that given a user-defined function from a byte to the current state to the next state, we can then just do all the new type wrapping and wrapping automatically using coerce. And that's a very handy feature of Haskell, which I really love. And then now using that, we can then define the C-style comments, which says, okay, here's our step function. The inputs are numeric because they're bytes instead of characters. Here's the current state, and then what's the state that we transition to on the right-hand side. And then we just coerce that to our state machine, and we're now ready to transmit that and serialize it to the C program that's going to run it. So this is the ugly part of the code where we need to actually marshal this, all this information across the Haskell to C boundary. And I don't expect you to understand this, just realize there's just a lot of unsafe and foreign stuff in pointer arithmetic here. And then once we just basically stick our lookup table, serialize it to bytes, pass it to C, run that C loop over the input, C passes us back a state, and we marshal that back into the corresponding Haskell type. So it's magic. You don't need to really worry about it, but this gives us a nice, purely functional API that we can work with now. Here's the full code example in case you ever want to run it. And so now we can test performance. So the way we can compile this is we first compile the C code using GCC, all optimizations on, and optimize for the current system's architecture. And then we're going to generate object code using the -c flag. So this will generate a run.o object file. And then we can link that against our Haskell program. So when we compile our Haskell program using GHC, if we provide the compiled object file on the command line, then GHC will link it in and satisfy the C call that the Haskell code expects. And then if we run the code, we've gotten back down to about 2.7 seconds. So it's faster than pure C. So that indicates that I must have been doing something wrong if wrapping it in Haskell made it faster. But it's still actually not as fast as the pure Haskell version yet. So we still need to do something else to make it go a little bit quicker. So that's what's going to be the subject of the next part, which actually uses the tricks described in the paper to make this much faster. Any questions before I go on to that? So yes, so the reason we're going to need to use C is that the next part of the talk is going to introduce a GCC intrinsic that we're going to exploit to simulate state machines very efficiently. And that intrinsic is not available from pure Haskell code. If it were, then I wouldn't need to wrap any of this in C. Yes. Any other questions? Okay. So the first question I have for all of you is, so how do we actually make a state machine parallel? How can we take advantage of multiple cores to accelerate this algorithm? Yes? Right. Right. So the idea is that, let's say I have a large text file, maybe gigabytes large, and I want to divide that text file into chunks. Right? So maybe 1 gigabyte here, 1 gigabyte here, and so forth, right? I would like to process each chunk in parallel, right? But when I'm beginning to process the second chunk, I don't yet know what's the final state for the first chunk can be, because we're doing things in parallel and the first chunk hasn't finished yet. So I need to actually be able to simulate all possible starting states for that second chunk, and for any chunk really. So that when the first chunk is done, I can then go, okay, so for this possible starting state, that would correspond to this ending state for that chunk. And we can then just chain them together. The problem with that, though, is that if you're simulating 16 states, then in order for this to actually be a performance win, you would need at least 16 cores to just break even with the serial code, and more if you actually wanted to get a performance benefit. And most machines, particularly like our laptops, don't actually have 16 cores to accelerate this algorithm. So the first insight from this paper, though, is that we actually can simulate 16 states much more efficiently using a CPU instruction which is wrapped in this case, a GCC intrinsic. This intrinsic is called built-in shuffle. And the best way to understand built-in shuffle is to make an analogy to how the Haskell code would work. So we're going to revisit our original transition type, which is a function from a state to another state. And this function can be actually can implement Haskell's monoid type class. And because if you're not familiar with monoids, a monoid represents something that can be combined and also has some default empty value. So for example, for a function, the default empty value would be the identity function where every state transitions back to itself. And if you're combining two transition functions, you compose them end to end using the composition operator. And again, if you're not that familiar with Haskell, Haskell provides an infix operator, these little angle brackets, synonymous with the binary mappend function. So mempty is exactly equivalent to our previous identity transition function. And so to understand built-in shuffle, it's basically a really fast mappend for transition. But we can only use it in C. We can't use it in Haskell. So that's why if we can push more logic into C, we can exploit built-in shuffle to mappend transition arrays very, very quickly. So we're going to translate everything we've done so far entirely into C. So this type right up here, V16SI, I probably should have named this something better. I was just cargo culting from the GCC manual on how to use the SIMD instructions. Probably should have called this transition. But anyway, this type, just anytime you see this, just think transition. So this represents a transition array or a lookup table encoding a transition function. It has 16 values in it, one for each possible transition. Our contrived transition is basically, this is the exact same as the serialized format of our Haskell transition function. And same thing, our identity transition array is just each state transitions to itself. So built-in shuffle is exactly equivalent to composing two transition arrays end to end very efficiently. So for example, let's say I'm starting on state 0. So I apply the contrived transition array once, well, I still transition to state 0. If I apply it again, I still transition to state 0. So that just stays 0. A more interesting case is, let's say I start on state 1, and I apply the contrived transition array once. According to that, state 1 should transition to state 4, which would be over here. And now if I apply it again, state 4 should transition to state 2. So the final state here would be state 2. And we can repeatedly do that for all possible 16 input states, and that's essentially what the built-in shuffle function is doing for us. It's chaining transition arrays. And built-in shuffle has, and also if we, for example, if we chain the contrived transition array with the identity transition array, we just get back the same contrived transition array. We can compare this to Haskell just to make sure that it behaves the exact same way. So for example, if I have a contrived transition function, and on the Haskell side, I compose it with itself, and then serialize that, I get the exact same result as if I had, oh, sorry, you have a question? It's just like what? Yes, it's a permutation computation, that's correct. And that's why it's called shuffle. It's a way of permuting things. So here, if I take the two Haskell functions, the contrived transition function, and compose it with itself, this is still a function, and then serialize that, I get the same result as if I had serialized each one individually and then composed them using built-in shuffle. And then same thing for this example down here. If you're familiar with the monoid class, you know that instances of the monoid class are expected to implement certain laws. The first law says if you combine any value x with the empty value, you get back x. Actually, the first two laws say that. Then the third law says that the operator you use to combine values is associative. So we can parenthesize things in any way. As long as they have the same order, the result will be the same. We could just omit the parentheses and there would be no ambiguity about what it means. And the cool part is that built-in shuffle obeys the exact same laws. So if we compose the transition, any transition array x with the identity transition array, we're going to get back x. And built-in shuffle is associative. So if I combine the X and Y transition arrays and then combine that with Z, that'll give me the same result as if I combine the X transition array with Y combined with Z. Just insert parentheses into that sentence I just spoke. And so now we're going to restructure our C code to exploit built-in shuffle. And the main difference to the C code is that we no longer pass in a single starting state and return a single ending state. Instead, we're just going to simulate all 16 states in our C code using this built-in shuffle function. Our lookup table now has changed to, actually just look at this type right here. So it's still two-dimensional. It's just that one dimension is here, 256 possible input bytes. The other dimension is here, 16 possible, so one transition array per input byte, and each transition array contains 16 values in it. It's just stored a slightly different way. Because it's not stored, so these 16 wide SIMD arrays are not exactly C arrays, so we need to actually explicitly convert between actual C arrays and these SIMD arrays. So that's the main reason for this starting for loop here at the beginning and this ending for loop here at the end. They're just adapter layers. The actual meat of the logic is in this for loop right here, which says, okay, read the current input byte, and then look up in our table what is the transition array for this input byte, and then use built-in shuffle to combine that with our current transition array to get the new transition array. And if we just repeat that for the entire input, then we get a transition array for the entire input. And we've effectively simulated all 16 states at once. But we've done so in a way that's much more efficient than actually having to do 16 lookups into a table for every input byte. And we have to make matching changes to Haskell code. So now we're not passing in individual states, we're passing in transition arrays back and forth with the C code. But otherwise, it's the same concept. Here's the full example in case you ever want to run it. And so now if we run this, the performance has dropped now to 1 second to process the entire file. So what's really cool is that we can actually simulate 16 states faster than we can simulate one state using the naive algorithm, which is already pretty cool. You might have been thinking, oh, maybe we're going to simulate 16 states slightly slower, and then we're going to make up for it with parallelism. Well, actually, we're even faster even in the single-threaded case just by using this built-in shuffle intrinsic. I'm not entirely sure why it's faster. I could guess, but I'd probably be wrong. But the key thing is that the built-in shuffle corresponds to roughly one CPU instruction, and that instruction, I'm guessing, is more cache-friendly than doing a lookup into some table in an L1 cache. Maybe because these SIMD transition arrays fit into closer registers, I'm not totally sure. And so the main instruction that powers this is called pshuffb. It's short for packed shuffle bytes, or sometimes it's vpshuffb for vector packed shuffle bytes. So the way you enable this is through this -m SSSE3 flag that you pass to GCC. And if you look at the assembly output, you can see it's being emitted right here. So that's how you know it's working. If you don't see that instruction, then you're getting the slow equivalent path, which is not going to be faster than the naive lookup algorithm. And so now that brings us to the second insight from the paper. So we're already faster in the single-threaded case, but now we can exploit parallelism because now we're working with transition arrays instead of individual states. So what we can do is we can take our inputs. So for example, let's say we have chunks right down here, chunk 0, chunk 1, ... chunk I. We can run our C code on each byte chunk into parallel. And the result of running the C code on each chunk is a transition array. So if we have n threads, we split it into n chunks, and we get n transition arrays. And because transition arrays can be marshaled back into Haskell as a transition function, we can then, if there's a small number of them, we can just cheaply compose all that functions to get our final transition function for the entire input. And usually the number of threads will be 4. So even though composing functions in Haskell is not as efficient as built-in shuffle in C, we only have to do it 4 times. It's still cheap on the order of magnitude of what we're trying to do. So the way we do this is we just have some function which chunks bytes into multiple chunks. This is a fairly standard function, which I'm not sure why it's not provided by the bytestring library. And then we have a function called runParallel, which is the same as our original run function, except now it takes an additional argument specifying how many threads to use, and therefore how many chunks to divide the bytestring into. And then we just use the high-level control.parallel library, which says, okay, just map this run function in parallel over all these chunks that we split the input into, and then combine them at the end using mconcat, so using the transition monoid. And then we're done. We've now just turned our C code into a parallel C code. Here's the full example. The main thing to note here is that there's one change I've made in this besides what I've described so far, is now we're just using mmap, so we can also read and access things lazily from the disk more efficiently. But that doesn't really affect performance that much. It's just there for completeness. The other thing we've done is we've made it so we can actually parameterize our program on how many capabilities. So we'll use whatever RTS option we pass on the command line to specify how much parallelism to use. So we can benchmark different amounts of threads. And so if we run this, we can see, okay, so for one thread, it's still the same performance as before, as a serial case. That's what we expect. For two threads, it's faster. Not quite twice as fast, but it's a decent performance improvement. So we went down from 1 second to 600 milliseconds. And if we turn on 4 threads, not 4 times as fast, but it's still a little bit faster. So it goes down to 444 milliseconds. So now our throughput is about over 2 gigabytes per second. And the reason why the parallelism starts to taper off as we add more inputs is that access to the disk starts to become the bottleneck. Because disk can, like if it's a hard disk, for example, then there's a finite number of spindles that it can read from. I don't know exactly how parallelism works for SSD, but I tested this in the case on a hard disk. So in that case, it's just the disk becomes a serial bottleneck. So there's a limit to how much parallelism you can extract, but it's still a performance win here. And maybe if there's a system that allows for much more efficient parallel disk access, then you could get even more parallelism wins here. So, but what's cool about the paper is they don't actually, oh, sorry, do you have a question? Yeah. This tilde right here in the where clause is a lazy pattern match. So it would be, this basically means that when you compute this, it's actually not going to force that tuple just yet. I'm actually not sure it's even necessary. I actually don't even remember the original reason why I did this, but I think it's just so that, just to not be unnecessarily strict. Because we only call this like, maybe 4 times if there's 4 threads, right? So there's no point, being extra strict when we don't need to. Sorry, what was the question? Something about the safeguard for null bytes is...
Yeah.
Oh, yeah, there may be... Yeah, that's a good point, actually. I hadn't thought about that. I didn't actually... That's a really good reason why you should have a lazy pattern match, although that probably wasn't the reason I did it. So I think, yeah, for the benefit of people watching the recording, he mentioned that this pattern match, but I feel it should be a type error in that case. Like, I don't think like the lazy pattern match should save you from a type error. I will have to think about that some more. Anyway, well, it compiled, so I'll have to think about that a little bit more after the talk. So anyway, oh, sorry, I forgot to even, going back to here. So the key thing about the paper is that so far we took advantage of the associativity property of the transition monoid, so we could parallelize things at the Haskell level. But we can also take advantage of the fact that if built-in shuffle is the C analog of the mapend on the Haskell side, and built-in shuffle is associative, then we can also take advantage of parallelism on the C side too. But what we're not going to do is we're not going to use several threads in the inner loop of the C, but instead we're going to exploit instruction-level parallelism that's automatic by the CPU. But the only way we can exploit instruction-level parallelism is if we reorder the way that we shuffle things using the built-in shuffle operator. So instead of reading 1 byte at a time and then composing 1 transition array at a time, we're going to read in 7 bytes at a time, and we're going to build up a balanced binary tree of built-in shuffles so that we actually reduce the number of data dependencies in our code. And if we do this correctly, then the CPU will actually notice that, and it will exploit those independent data accesses to do speculative execution, and we get instruction-level parallelism that day. Because it can tell that, so essentially what we're going to do is we're going to read all 7 bytes. That can be done in parallel. There's no data dependencies there. We can compute the transition array for all 7 of those bytes. That can be done in parallel. No dependency there. And then when we're doing the first level of this tree, these 4 intermediate transition, so each of these nodes represents 1 invocation of built-in shuffle. So we take those 8 transition arrays, we use 4 built-in shuffles to reduce them to 4 intermediate transition arrays. Those can be done in parallel. Then we use 2 more built-in shuffles to reduce those to 2 transition arrays. That can be done in parallel. And then we do 1 last built-in shuffle to get a final transition array for those 7 bytes. And then, so basically the critical path, the serial bottleneck, is the height of the tree. You may think, okay, why don't we do this for like 31 bytes at a time or 63 bytes at a time? And the answer is like you get diminishing returns. So after about 7, I haven't seen any significant speed up. So I just stopped there. So here's the example code to do that. The main thing that changed here is this inner loop, where basically each comment marks 1 level of that tree. This is the part where we're reading each input bytes. This part's done in parallel. These 4 built-in shuffles are done in parallel. These 2 built-in shuffles are done in parallel. And this 1 built-in shuffle is done in parallel at the very end. And if we time that, we notice a few things which are interesting. One is that we're getting a speed up even in the single-threaded case. So we're actually getting parallelism using 1 core, but now it's parallelism at the CPU level. So we went down from 1 second to 700 milliseconds. And then if we turn on additional cores, we're still seeing a speed up compared to the old case. It's not as significant, but it's still there. So we went down to, in the case of 4 cores, 386 milliseconds for processing 1 gigabyte of input. This comes out to about 2.6 gigabytes per second, or about 3.8 times faster than our best pure Haskell implementation. And I'll conclude by saying that I've only talked so far about how to do this for 16 states. The original paper shows how to generalize this algorithm so it can process up to 512 states. The only reason I haven't talked about that or implemented it is that there was no GCC. It requires an additional CPU instruction, which is not, as far as I can tell, is not yet wrapped in a GCC intrinsic. So you have to program directly in assembly in order to take advantage of it. I just didn't want to do that. And the second, but everything I've described so far, so for 16 states, is up on GitHub in a package, a Haskell package called SIG, short for Blazing Fast Signature Detection. The main thing I want to point out is the way that the paper gets from 16 to 512 states is by also still exploiting the associativity property of built-in shuffle. So the entire gist of the paper is that you can take advantage of associativity to get more and more parallelism. So associativity is not like this ivory tower, thing for compositionality and maintainable programs. It's also a useful concept for just writing really efficient, highly optimized programs too. The second takeaway I want you to get from my talk is that Haskell is actually a great language for providing a high-level interface, a purely functional interface to C code. And we saw that sometimes you can actually just speed up your C code when you wrap it in Haskell compared to the pure implementation. So Haskell and C is actually a great combination. I recommend trying it out if you haven't done so already. And so if you ever want to find these slides so you can review them or run the examples I described, there's a link here, and I'll try to make sure that if there's a recording of this talk, that includes also the link to the slides as well. And that concludes my talk, if you have any questions. Yes? No, I did not try that because I actually don't know. So the question was, have I tried wrapping that CPU instruction in intrinsic, either in C or in Haskell, and using it that way? PC says he's had success doing that for pop count, for example. No, I haven't done that because actually I don't know how to do that. So if somebody knows how to do that, I would greatly welcome that. Or just teach me how to do it and I'll do it too. Yes? No, this is purely a toy project. I just wanted to implement the paper to just basically to convince myself it was real and it gave performance improvements, and also so other people could build upon it if they knew how to generalize it to the full number of states. Yes? Is there a way to include type-safe transition state functions? Not that I'm aware of. I believe this is restricted primarily to informationless state automata, meaning that you can't associate any information with each state. Unless there's some way that you can compile your more descriptive state representation to the more simplistic, minimalist state representation, then I'm not sure if there's a way to do that. Yes? So the question was, can you use the same technique for non-deterministic finite state automata? So there's I believe you can naively translate NFAs, so non-deterministic finite state automata, to deterministic finite state automata by exponentiating the number of states. So if you have an 8-state NFA, then you can translate that to a 2 raised to the 8 states, which is what 256 state DFA. So you could if you have, let's say you actually implement the paper and you have like 512 states, right? Then you can naively simulate any 9-state NFA automata. To do something more efficient, you would need to have a more efficient translation process for the non-deterministic finite state automata to the matching deterministic finite state automaton. Oh, so the question was, yeah, I mean, CZ said you're running all the states in parallel. Isn't that essentially a non-deterministic finite state automata? I'd have to think about that more. Like, I'm not sure if doing that would mean that you lose the parallelism property. I don't quite know the answer to that. I'm not sure. Yes. Oh, can you use this to compile regular expressions? Yes. So regular expressions can be compiled. So first they can be compiled to NFAs, and those can be compiled to DFAs, which is what this algorithm uses. So then it's just a matter of how many states the DFA can simulate. So 512. So it would be like you could naively translate small regular expressions to this algorithm. Larger ones, I'm not sure. You need like a more efficient encoding. Like in the C example, like sometimes there's a much more efficient way to implement as a DFA than the naive way you would encode a regular expression. So yes, it is possible. It's just the limit is the number of states that this can simulate. All right, I think there's no more questions. Thank you very much.